Using Newton's method to find the roots of a polynomial is really rather straightforward. We'll be using the definition of the slope and explore the usefulness of the first derivative. Here are 4 easy steps. First, randomly guess a number, any number. From there, form a tangent line. Then, form another tangent line. Finally, we hone into the solution. I'll start by using a simple second-degree polynomial or quadratic function. The graph is a parabola, like so. Now we simply pick a random point and call it x sub 0. For now, we'll find the solution to the point on the right-hand side. The first derivative at x sub 0, we call this f prime of x sub 0, is also the function of the line tangent to f of x at x sub 0. This tangent line has the basic definition of delta y over delta x, or a change in y direction divided by the change in the x direction. To quantify this, we have delta y is just f at x sub 0 minus 0. This is just the height of the triangle. And delta x is x sub 0 minus the point where the tangent line intersects the x-axis at x sub 1. Solving for x sub 1, we have this formula. Now, x sub 1 becomes the point to draw the next tangent line for next iteration. The process is to use the new x sub 1 for subsequent iterations and repeat until the tangent line gets closer and closer to the actual solution. And we can now summarize that x sub n equals the following generalized formula for x at any nth iteration. This is how Newton's method works. We derive Newton's method for x sub n, but the formula is more commonly written as x sub n plus 1. Both formulas are the same, that the current iteration depends on x from previous iteration. Now, what if the initial guess x sub 0 was so large that it seems impossible to converge? Well, the fact is, it doesn't matter how bad or how large the initial guess was, as long as the slope evaluated at any given x value does not equal to 0, Newton's method is going to work. In other words, as long as the tangent line is not a horizontal line, this is going to work. Remember, a quadratic can have up to 2 solutions. To find the other solution, randomly select a number for x sub 0 coming in from the left-hand side. Let's use a relatively large negative number such as x sub 0 equal to negative 100. This way, we hone in to the second solution from the left-hand side. And one more note before we jump onto Microsoft Excel. Newton's method can be applied to higher-order polynomials. For example, for this cubic function, or third-degree polynomial, there are 3 roots. To use Newton's method, we need to pick 3 initial guesses, x sub 0s, close to their roots so they'll all converge. Now let's put Newton's method into an Excel spreadsheet. We'll let the user input any random coefficients a, b, and c. For now, we'll simply use the numbers 2, -5, 2 for the values of a, b, and c. Likewise, x sub 0 is also an input for the user. This light blue color represents an input for the user. This f prime of x is the first derivative of the function with the above coefficients, and is simply 2 times the a term for the b term, and the c term is equal to the b term of f of x. Now, using the quadratic formula, we know that the function f of x has solution, or roots, of 2 and 0.5. Here's a quick recap of the quadratic formula. The three pictures are graphs of f of x with different ranges. They're zoomed in at various levels. The graph on the bottom is the most zoomed in. Cell B5 here is where the user inputs an initial guess x sub 0. Columns A and B show the iteration results from x sub 0. X sub 1 uses the result from x sub 0. X sub 2 uses the result from x sub 1, so on and so forth. The value for x sub 1 is simply Newton's formula, the previous x term minus the function f divided by f prime, both evaluated at the previous x sub 0 value. For x sub 2, we're doing the same thing, except this time we're using the result x sub 1 from the previous iteration. The formula repeats for all subsequent iterations. As shown, using an initial random guess x sub 0 value of 100, we can see that by the 11th iteration, Newton's method converges to the solution value of 2. If we had used an initial guess x sub 0 of 10, the solution converges at the 7th iteration. Now for the other solution, we use a random negative x sub 0. As mentioned, let's try x sub 0 equals negative 100. Here you can see that by the 11th iteration, it converges to an x value of 0.5. The graph also shows the solutions at 0.5 and 2, where the parabola crosses over the x-axis. And remember, we can also factor this quadratic formula by hand, like so. And we can find the solution this way. Now let's try a different quadratic function. A, B, and C has values -2, 8, -5, respectively. Let's use x sub 0 equal to 100. Now let's try x sub 0 equal to -100. Newton's method converges to a value that matches the values using quadratic formula, and the graphical view where the parabola touches the x-axis. They all check out. For the scope of this video, we will keep to real solutions. For instance, when A, B, and C equal 3, -3, and 1, respectively, we'll get a parabola with no real solutions, as the parabola will never cross the x-axis, like so. But let's get back to polynomials with real solutions. Suppose A, B, and C equal 10, 5, -20, respectively. X converges to our solution. Next, let's try A, B, and C as -99 to 100 for A, B, and C, respectively. Here we see convergence again. Now let's try A, B, and C as 2, 50, 300, using the value of x sub 0 equals to 100 and -100. As expected, we see convergence at -10 and -15. Here the bottom graph is not showing up because it is outside the preset range. And finally, we'll put Newton's method into Python and allow the user to enter coefficients a, b, and c and x sub 0. We'll use the same quadratic function as before, where a, b, and c equals 2, -5, 2, respectively. We'll run it twice, once for x sub 0 equal to 100, and once more for x sub 0 equal to -100. This also gives a result of 2 and 0.5, with a tiny error due to the large number of significant figures carried out within Python. Wow, that was so cool. And in conclusion, we see that Newton's method is a powerful yet straightforward way to find solutions to polynomials. I hope you enjoy this as much as I did. Thanks for watching.